Hey everyone! So today, we're going to pull back the curtain on one of the most powerful tools in all of machine learning, regression. We're going to see exactly how the apps on your phone learn to predict the future, from tomorrow's weather right down to your pizza delivery. Have you ever just stopped and wondered how the apps on your phone seem to know what's going to happen next? I mean, how can they give you such a precise number for something that hasn't even happened yet? It's kind of wild, but it turns out they all rely on the same fundamental idea.
Just think about it for a second. Your food delivery app tells you your order will arrive in, let's say, 23 minutes. Not about 20 minutes, but exactly 23. How in the world does it land on that specific number?
Or what about those real estate websites? You type in an address and boom, it gives you an instant estimated value for any house on the market. It feels like magic, right? But where do these numbers actually come from?
And of course, the classic example, your weather app confidently telling you it's going to be 72 degrees tomorrow. Well, all of these seemingly magical predictions, delivery times, house prices, temperatures, they're all powered by the exact same core technique.
Well, that technique is called regression. And you know what? At its core, the idea is actually super simple. It's all about teaching a machine how to predict a specific number.
Now, this is a really important point. Regression isn't for predicting clean categories like, is this a picture of a cat or a dog? It's all about predicting a number that can be anything on a spectrum, a price, a temperature, a quantity. Basically, if you're asking how much or how many, you're probably looking at a regression problem.
And you know what's cool? This is something you already do, probably without even thinking about it. When you look at a used car, your brain performs this little regression on the fly. You take in all these factors, the mileage, the age, the condition, and you use all your past experience to land on a final number, its price. A regression algorithm is doing the exact same thing, just, with way more data and at lightning speed.
And believe me, this isn't just for cars or houses. It is everywhere. You see it in finance with people trying to predict stock prices. It's in healthcare, estimating how long a patient might take to recover. Marketing teams use it to forecast next quarter's sales. Seriously, it's one of the true workhorses of the entire data science world.
Okay, so a machine can't just get a feeling about the price, right? It needs something concrete. It needs data. So let's break down the actual building blocks that make these predictions possible.
All right, let's get some of the vocabulary out of the way, using our house price example to make it easy. The inputs we use, the things we know, like the square footage, number of bedrooms, and age of the house, we call those features. The final number we're trying to predict, in this case the actual sale price, that's our label. And all the examples from past sales we show the machine, that's our training data.
So, okay, how does the learning part actually happen? Well, it's a process called model fitting. The algorithm just chews through all that training data, and its one job is to find the hidden mathematical pattern that connects the features to the label. If you picture a graph with a bunch of dots, model fitting is basically the computer trying to draw the one perfect line or curve that gets as close as possible to all those dots. It's finding the trend.
But here's the thing. Not all data looks the same, right? Sometimes the pattern is a straight line, sometimes it's a curve. So it's best to think of all the different regression algorithms as a toolkit, with each tool being specially designed for a specific kind of job.
And the first tool you'll almost always reach for, the hammer of this toolkit, is linear regression. This is your go-to starting point. It works on a really simple idea, that there's a straight line relationship in the data. As one thing goes up, the other goes up or down in a really consistent way.
But what happens when things get messy? Like, what if you have dozens, maybe even hundreds of different features to look at? That's where smarter tools like Ridge and Lasso come in. Ridge helps make sure the model doesn't rely too much on any one single feature. But Lasso has this awesome superpower. It can look at all your features and decide which ones are useless, shrinking their importance all the way down to zero. It's like an automatic cleaner for your data.
Okay, now for something completely different. Not all tools try to draw a line. A decision tree is more like a game of 20 questions. It builds a flowchart of simple yes or no questions to get to the answer. It'll ask something like, okay, is the square footage over 2,000? Yes. All right, is it in the downtown neighborhood? Yes. Okay, then I predict $450,000. It's a really intuitive way to capture complex rules in your data. Okay, so that's a lot of tools. How in the world do you know which one to pick? Well, this little cheat sheet here is your best friend. If you need a simple, fast starting point, linear, every time. If your data clearly follows a curve, that's a job for polynomial regression. Got way too many features and worried about complexity? Lasso or Ridge will help you out. And if you need to capture complex rules and want a model that's easy to explain, a decision tree is a fantastic choice.
All right, so building a model is one thing, but knowing if it's actually any good, that's a whole other ballgame. So let's talk about how we can grade our work and how to avoid the #1 mistake almost everyone makes.
So how do we put a score on our model's performance? We use something called error metrics. Mean absolute error, or MAE, is super simple. It just tells you, on average, how far off your predictions are. If your MAE is 10, it means that on average, your predictions are off by about $10 or 10 degrees. Mean squared error, or MSE, is kind of similar, but it hates big mistakes. It really punishes those embarrassing, way off predictions. And R squared. That gives you a percentage. It tells you, hey, how much of what's going on here can your model actually explain?
But now for that big trap I mentioned. It's called overfitting. This is what happens when your model gets, well, too smart for its own good. Instead of learning the real general pattern, it just memorizes the training data, including all the random noise and weird quirks.
Honestly, the best way to think about this is like studying for a test. The overfitting model, that's the student who just memorized the practice questions word for word. They'll get 100% on those, but give them a new question they've never seen before, they totally freeze up. A good model, though, is like the student who actually learned the core concepts. They can handle anything you throw at them because they understand the why.
It all boils down to this fantastic quote. An overfit model has learned the noise, not the signal. Basically, it's getting distracted by all the random, meaningless junk in the data instead of seeing the real, important pattern that you actually care about.
Okay, so with all these different tools and these tricky pitfalls, you might be wondering, where do I even start? Well, the good news is, there's a really simple, really effective strategy that pros use all the time.
Here's the game plan in 3 simple steps. 1, always start simple. Kick things off with linear regression. It's fast and it gives you a great baseline. 2, diagnose. If it's not working well, be a detective. Figure out why. Is the data actually a curve? Maybe you should try polynomial. Do you think a bunch of your features are useless? Try lasso. And 3, iterate. Now that you know the problem, you can pick the right, more advanced tool from your toolkit to fix it.
So there you have it. From predicting your pizza's arrival time to forecasting the stock market, regression is the engine that turns raw data into real, powerful numerical predictions. It's this amazing blend of clever math and just real-world usefulness. So now that you've got the toolkit, my question for you is, what are you going to predict first?